Hello, hello everyone. My name is Ke. Today we'll be introducing our program for the diamond market. This page will mainly divide into four parts: market background, data processing, model building, and business insights. Firstly, let's move to background part. Diamond valuation has traditionally been a complex and subjective process, which may result in price uncertainty and may also lead to fraud in the market. One of the reasons is due to the complex transaction channels, including jewelry stores, wholesalers, and so on. Another reason is that the price valuation of the diamond relies heavily on the expertise of the diamond expert. It is a highly specialized job that requires experts have an excellent understanding of the factors affecting diamond price, market trends, and inspection methods. However, with the development of digital technology, the emergence of various machine learning models have made it no longer difficult to accurately predict diamond prices. Now let's move to how to do that. The first step is definitely data processing part. Our research data set consists of 9 factors that could potentially impact the price of diamonds, including carat, cut, color, and so on. After knowing that, we did some data cleaning. First, we removed the irrelevant feature to simplify our data set. Next, we detected and removed the data points with zero values, as such values are not realistic. Subsequently, we address outliers in our dataset. Given the large size of our dataset, we needed to define suitable criteria of exclude these extreme values. These operations made our dataset more reliable while retaining a sufficient number of data points for analysis. Next, welcome my partner to have a speech.
So in the original method, the categorical variables such as diamond colors were indicated by assigning them to a sequence of integers from 0 to 6, which would mislead the linear regression model. To address this issue, we have adopted the use of diamond variables. Additionally, we have removed the original categorical variables from the dataset to maintain model integrity and eliminate the bias. Referring to the displayed chart, the initial regression model yielded an R-squared value of 0.92, indicating strong explanatory power. Additionally, observing the p-values of the independent variables, which are all nearly 0, indicates that all variables are statistically significant. We also enhanced the correlation matrix. Looking at this heat map, the intensity of the color of this chart correlates with the strength of the relationship between each variable and the diamond price. A darker shade indicates a more robust positive correlation. Conversely, a light shade suggests a weaker influence on the diamond price, which could indicate less change or even a potential negative correlation. We also use LISO and ARRAY for regularization, which resulted in an accurate increased mean squared error comparing to the previous model's metrics, indicating that the initial model was potentially overfitting, as the regularization process tends to increase error on the training set while aiming to enhance the model's generalization to unseen data. We also employed k-fold cross-validation, splitting the data into 5 distinct subsets, with each fold showing reliable mean squared error scores. And we also obtained an average mean squared error of standard deviation that confirmed stable model performance. To refine our model's predictive accuracy, we use the method of interaction terms. This approach enriched the model's complexity and significantly improved the R-squared value. The increase in R-squared value demonstrates that the model's explanatory power has been enhanced, and we can also optimize the model's predictive ability. We also plotted 2 plots based on the residuals to evaluate the model performance. The right regression line shows the general trend of the predictions concerning the actual values. However, the prediction accuracy of the model might be revised. The model appears to under-predict higher actual values. Similarly, the model overpredict some of the lower actual values. Additionally, the variance of the residuals may increase as the actual value increase, which suggests that there may be heteroscedasticity, violating the assumption 5 of multiple linear regression that residuals should have constant variance across all levels of the predictor variable. The right-hand side plots also proves this point of view. These residuals are not randomly distributed around the horizontal line I0. Now let's move on to the decision part.
As for the decision tree model, we use original dataset, not the one with dummy variables, to keep the model simple for building and interpretation. After splitting the dataset into training and testing, we then feed the model. The decision tree model's mean squared error is approximately 520,000. Decision trees can be prone to overfitting, especially when they grow deep. Therefore, we conduct k-fold cross-validation to find the optimal depth. The optimal depth is 11, where negative MSE is maximized. The test MSE after improvement is reduced to around 309,000. Additionally, we set mean sample sleep to 8 and mean sample split to 15. This ensures the model will not capture too much noise and overfit the predictions. We then plot a part of the tree by limiting the depth at 3. We primarily focus on decision tree branches with the smallest square error. When the diamond weight, which means carats, is around 0.995 carats, the width of the diamond is 4.99 millimeter, and the length of the diamond is 4.63 millimeter. The decision tree would give us an average diamond price of around $788. As we can see, the MSE after pruning has been further improved to around 387,000, and R-squared of the model is 97.5%. To evaluate performance of our prediction results, we implement a learning curve. Based on the learning curve, the red line shows the model's training accuracy, improving as more data is used. The high training score of 0.98 confirms a good fit to the data. The green line represents cross-validation accuracy on unseen data. More data enhances the model's ability to generalize. Meanwhile, these shaded areas reflect some score variance, with low variance indicating reliable estimation. The convergence of two lines also indicates improved performance, as there are no signs of overfitting or underfitting the model. Feature importance analysis also indicate carat occupies the most crucial weight, which represents carat has a significant impact on diamond price prediction. Moreover, the width, clarity, and color also account for some proportion of the importance. However, other factors have little impact on the diamond price. We continue to look at the residual plot. Unlike the plots in the linear regression model, these residuals of decision trees are more evenly scattered around zero, indicating consistent error variance across predicted values. There's no clear pattern in residual patterns, reducing the likelihood of nonlinearity or model issues. While there are some potential outliers that aren't as extreme as before, this all indicate the decision tree performs generally well and is free from bias. For improvements of the model, we enhance the model by applying a random forest. Since random forest consists of multiple decision trees, we only pick one of the trees within the model and print it out. Similar to the decision tree model, the variables that affect diamond price most significantly are still carat, width, and clarity, with the optimal combination having a squared error of around 56,000. The MSE of the random forest model is around 290,000, with an R-squared of 98.12%. Random forest has improved by a small margin compared to the single decision tree. Next, my partner will continue to talk about artificial neural network model.
So in the initial stage of the developing our artificial neural network model, adjustments to the layer size and learning rate did not obtain satisfactory results. So we decided to proceed optimize techniques with TensorFlow to enhance the model's performance. This strategy approach led to marked improvements in our metrics. The final mean squared error was crucially reduced and the R-squared value increased, which indicates a stronger correlation between the predict and actual values, and therefore a more satisfactory model performance. Looking at the left side two scatter plots, the model performs well for lower to mid-range values, but shows variability in performance at the higher end of the actual values. There is no clear evidence of bias, but the model's accuracy will decrease as the value of the target variable increases. The second scatter plot indicates that the residuals are centered around zero, which is good because it suggests that the model does not overpredict or underpredict the range of the observed values. However, the spirit of the residuals appears to increase as the observed value increase, which indicates heteroscedasticity in the model. We also prepared the validation loss curve. The two lines converge quickly and then continue parallel, indicating that the model is generalizing well. Additionally, the model could quickly reach a low and stable loss with seldom overfitting or underfitting, suggesting that it performs well for the training data.
Better predict diamond prices, we try 3 different machine learning models. We use MSE and R-square as 2 indicators to evaluate the performance of the models. After comparison, we found that the random forest model was the best, with the smallest MSE of around 290,000 and a largest R-square of 98%. Through the optimal random forest model, we can get some business insights, which are beneficial to the operation of the company. Firstly, the R-square result of the model means that it can explain 98% of the diamond price changes. This means that if there are some new or unpriced diamonds, we can use this model to estimate their market value and avoid price deviations or frauds caused by lack of professional knowledge or market information. For diamond appraisal agencies, they need to test and evaluate a large number of diamonds, and this model can provide them with a more fast and accurate diamond price estimation tool. The weight of the diamond is the main influencing factor, and it is positively correlated with the diamond price. That is, the larger the weight, the higher the price. This means that the company should prioritize the purchase and sale of larger diamonds to obtain higher profits. At the same time, the company should also pay attention to the market demand and preference. Different consumers may have different expectations and budgets for the weight of the diamond. The company could use market research and data analysis to formulate appropriate pricing strategies and promotional activities of different target customer groups. For example, the company could target high-end customers and launch diamonds with a weight of more than 0.995 carats to show their rarity and luxury, and target mid-range customers and launch diamonds with a weight of 0.625 carats to 0.995 carats to balance their price and quality, and launch diamonds with a weight of less than 0.625 carats to meet their economic and practical needs. The size of the diamond is also an important influencing factor, and it's positively correlated with the diamond price. This means that the company should pay attention to the carting process of the diamond to ensure the size and shape, which will affect the luster and beauty, and thus affect the consumer's purchase intention and satisfaction. Firstly, the company can introduce advanced carting equipment and technology to improve the carting quality and efficiency. Secondly, train and assess to improve the scales and level of the diamond of cutter, thirdly, design and innovative to develop different diamond shapes and styles to meet the preferences and needs of different consumers. For example, launch different diamond shapes to suit different designs and styles of rings, necklaces, earrings, and other jewelry. The clarity of the diamond is also an important influencing factor, and it is positively correlated with the diamond price. This means that our company should value the quality and inspection of the diamond to ensure the clarity and transparency, and thus affect the consumer's trust. The company can use international standards and certification to evaluate and prove the clarity and transparency. So this is business insights we got from the model. Next, let's move to the conclusion part.
Thanks, my partner speaking. In conclusion, the MSE values of 3 models are very large, and the main reason may be that the performance of the original data is not good enough. By comparing the prediction capabilities of 3 models, we finally selected the random forest model, which largely solves the complexity and the subjectivity problems of the traditional diamond market and brought obvious commercial value to the company. And at the same time, we also suggest the company pay attention to market demand and the preference of different consumer groups and put forward different business suggestions based on the 3 factors that have greatest impact on diamond prices: carat, weight, and clarity. And this is all for our presentation. Thanks for watching.